Unit 5, Lesson 2, we're going to start by finding a quadratic function. So we're going to create a quadratic function given the vertex and one point that the function passes through. So the vertex is at 3, 5, and we have a point of 1, -3. Now what I want you to write down is this general equation. This is the vertex equation. And so what we're going to do is we're going to replace the 3 here. Remember, it's a positive 3, so inside it's going to lie to us, and it's going to tell the truth in back. Now, we're given an extra point. This is the x value and the y value of a separate point that occurs on this function. So x will go here with the 1, and y will be -3 for the y. -3 equals a times the quantity, 1 subtract 3 quantity squared plus 5. And now I'm going to isolate to solve for a. Subtracting 5 from both sides. -2 times -2 is +4. Dividing, and a equals -2. Now I need to go back to the original problem. And the only two variables you should see in the original problem is a y and x. So this is what I'm going to write down. But in place of the a, I'm going to put down a -2. And there's example number 1. Let's look at example 2. Let's look now at example number 2. All right, so we're going to start with that general equation. We have y equals a times x minus h quantity squared plus k. So I'm going to replace the vertex goes in here. So notice how it's a -2. So it needs to be the opposite symbol inside. It lies to me. It tells me the truth. Now I'm going to replace y and x with this additional point that the function passes through. 7 is your y and 2 is your x. Let's solve for a. By solving, we're going to do PEMDAS backwards. So on the side that contains a, we're going to do adding or subtracting first. Then next is going to be multiplying or dividing. By the way, 4 over 16 divided by 4 is 1/4. And now I'm going to rewrite it. So I'm going back to this form and replacing the a, in this case, with 1/4. Your final answer should have both an x and a y. From this part of the learning objective is our third and final example here. So I'm going to start by writing down that general equation, y equals a times x minus h quantity squared plus k. Always replacing the vertex, it lies to us, so x plus 1 quantity squared plus 3. And now I'm going to replace the x and the y. So here's my x, and here's my y. And let's now solve for a. Doing PEMDAS backwards. So PEMDAS backwards looks like first getting rid of adding or subtracting. Then get rid of multiplying or dividing. And now we're going to rewrite from this form. I'm going to replace the a in this case with a negative or -1. And I'm done. So right now we are working with quadratic functions. Remember, quadratic functions look one of two ways. We have parabolas that open upwards and have a vertex down below, or parabolas that open up downwards and have a vertex up above. How do we find the vertex? Well, the x-coordinate of the vertex is found using this formula that you have to memorize. This is your a, b, and c in standard form. So if I asked you to determine the vertex without a calculator, here is a is 2, b is 8, and c is -3. And we can see this doesn't even contain a c. So my b is 8, my a is 2, and I have now the x-coordinate of the vertex would be -8 over 4. -8 divided by 4 would be -2. Now, a vertex has both an x and a y. So only achieving an x is not going to help. How do we achieve the y? We go back up to the equation, and we're going to substitute in a -2. So I have 2 times -2 squared plus 8 times -2 minus 3. Oops, I didn't need a parentheses there. Okay, so here we go. Let's evaluate this using PEMDAS. So is there work to do in parentheses? There is right here. -2 squared is 4. There's no work to do in parentheses here, no operation. Then we're going to do multiplying or dividing. 2 times 4 is 8. 8 times negative 2 is negative 16. And we have negative 8 minus 3, which would be negative 11. So what are the coordinates of this vertex? This is my 2, this is negative 2 is my x coordinate, and the y coordinate is negative 11. By hand, they want the algebraic form, not just plugging into your calculator and determining the vertex. Right, the very last problem. We're going to start by plugging this in the calculator now. So remember, anytime we have a fraction, we're going to hug it with parentheses. So I've done that, and now we have 3 different parts we're going to answer here. The height of a ball thrown by a child is given, where x is the distance in feet from where the ball is thrown. So x is the distance from where the child throws the ball, and then the height of the ball above ground is given by our y. Okay, so let's go out here and let's just do a zoom fit, and we can adjust accordingly. I don't need to know the negatives, so let's come back here. We don't need to know any of the negatives. We're going to adjust the y, and now we have a good idea what this looks like. Okay, the first question is, how high is the ball when it is thrown? How high the ball is thrown is representing what is this y-intercept. So remember, in standard form, this is our y-intercept. So we can see when I do second calculate and x is 0, we get 3.5. 3.5 is the same as half of 7. So the y-intercept, or the height when the ball is thrown, is, you could say 7 halves, or you could say 3.5. They are equivalent. The second thing is, how high is the ball when it's at its maximum height? So this is going to be the pathway of our ball above ground as it moves, right, with horizontal. So I'm going to figure out the maximum here. And I'm going to go somewhere to the left of the highest, press and enter, somewhere to the right of the highest, press and enter, and back to this height. Now we need to analyze this. This is the distance it went before it hit a maximum. The question is, how high is the ball? So the ball is 26 feet above the ground after it travels horizontally 15 feet. It's 26 feet above the ground. That's the key, right? And so how high is it? 26 is the maximum height. How far from the child is the ball when it hits the ground? So I want to know at this point right here. And so we could use the quadratic formula, but we do get to use the calculator here. So let's figure out this 0. So I'm going to go directly above the x-axis, going below, and you can see when it's below, and then back to as close as possible. And so this represents 0. Key, this represents 0. So the ball is approximately 31.12 feet away from the child when it hits the ground.